Anyone done any homework yet? One of these days, the answer to that question needs to be yes. Okay, this is a terrible piece of chalk. Okay. All right, well then, I'll just keep covering stuff. Ugh. Apparently this paper went for the copier crooked. Okay. So, last time I did spectral methods for periodic boundary conditions. So now I'll deal with the non-periodic case. Okay. All right. Now, in the periodic case, we represented a function by a Fourier series, but that doesn't work so well if your function doesn't satisfy periodic boundary conditions. So your function u of x is not super periodic, then Fourier series ek has a big problem, and that is does not converge to the actual value of u of x at every point. The reason being that if it is not periodic, then its 2 pi periodic extension is discontinuous. So, as an example, a well-known function called the sawtooth function, which really is just coming from u of x equal x. So if I graph u of x equals x on the interval from minus pi to pi, okay, but then for 2 pi periodic extension, I'm going to simply take this segment of the graph of u of x equals x and replicate it. So if I were to draw vertical lines in between, you would have the appearance of saw teeth. So at these points of discontinuity, this Fourier series will doesn't really have a correct value to converge to. Either one could be correct. What it does is it converges to the average. So at these multiples, really odd multiples of 2 pi, the series will converge to 0. So it's the average of the values of pi minus pi here. So that's one thing, is that this file doesn't converge at those points. And at other points, it does converge. convergence is slow. The reason for that is the more smooth a function is, the okay, the more smooth a function is, the faster these Fourier coefficients go to zero. So smooth functions, the Fourier series converges rapidly. Well, this is the opposite of that case. It's not even continuous everywhere, so the Fourier series will converge particularly slowly. One more bad thing, problem called Gibbs phenomenon. Gibbs phenomenon happens when you go ahead and use a Fourier series for a function like this, and you have to truncate it at a certain point. And what happens is, away from discontinuities, your truncated Fourier series will be a good approximation. But as you move closer to these points of discontinuities, you get behavior like this. These nasty high frequency oscillations that grow as you approach a discontinuity. So it's really not a good approximation to your function at all. So this is why we don't we try to avoid using Fourier series for non-periodic functions. All right. So instead of using trigonometric polynomials, which is what a Fourier series is, we can use regular polynomials. All right. What I'm going to say about Fourier series for this. With ordinary polynomials, there's no expectation of periodicity. But even then, we still have to be careful in terms of how we use polynomial approximations. Because back in the periodic case, we used a grid of equally spaced points. And of course, that's a natural thing to do. We did finite difference methods also, we used a grid of equally spaced points. So it's tempting to do the same thing here. But the problem with polynomial interpolation with equally spaced points bad idea. There's a famous example of this that's called Runge's example. And I would have shown this like in a class like 560. Your function is something like 1 over 1 plus x squared, or some variation of that. So you have something like this where the function behaves like that. So suppose you fit this with a polynomial of even modest degree, like say degree 10. What happens is, okay, so here's your function again. And your polynomial, if you interpolate at equally spaced points, your polynomial will pass through all of these points that sit on the graph. Okay. Problem is what happens in between those points. Near x equals 0, it's okay. But as you get further away from x equals 0, the error gets very large. This graph is terribly unsymmetric. So as you get closer and closer to the boundaries of your interval, the polynomial interpolant has extremely large error. So we're not going to do that. We're not going to use equally spaced points. You have a nice alternative though. Chebyshev points. Okay. Now, I'm going to focus on the interval -1 to 1, just for convenience. That's where the Chebyshev points are defined. If you're working on a problem on a different interval, then you would just do a scaling and shifting to move to that interval. Okay. All right. So the Chebyshev points find to be J's cosine pi j over n. And we have n plus 1 points altogether. So j goes from 0, 1 up to n. So when j is equal to 0, you have cosine of 0, which is 1. And when j is equal to n, you have cosine of pi, which is -1. So you're getting points from ranging from 1 down to -1. Okay. Now, these are not equally spaced. However, these angles as applied to cosine, pi j over n, those are equally spaced. The way to visualize Chebyshev points, how they're distributed. If I draw the top half of a circle, something vaguely resembling a circle, and then I mark equally spaced points along the circle, so equally spaced angles, best I can. All right. Then what you do is from the circle, you draw a vertical line down to the x-axis. And what you can see is because the circle, the curve is getting steeper as you approach the boundaries, the x values are clustering at the boundaries. So less spacing over here at the edges, more spacing in between here. And that works out nicely for an example like this, where we have large error at the boundaries. So if we were to use Chebyshev points for interpolating, we would have more points where the error is large. And that helps. It's still not a great approximation, but it's a lot better than that, certainly. Okay. Oh. Okay. A question about Chebyshev points. All right. All right, so what we'll do is, for a function u of x we want to take a derivative of, as before, the approximation of a derivative is the derivative of the approximation. So we will construct a polynomial that matches u of x at the Chebyshev points, and then we'll take the derivative of that polynomial. Exactly. So our function u of x of 1 triple eight is approximated by our tripling polynomial, which is called Pn of x. The subscript, when you have a tripling polynomial, typically the subscript that you give to it is the degree. Now we have n plus 1 interpolation points. The degree will be 1 less than that, so n. And I'm going to write that in Lagrange form. So the coefficients are just our function values. So uj is equal to u of xj, the value of u at the Chebyshev point that I defined earlier. And these are Lagrange polynomials for all our Chebyshev points. Okay. Now, I believe all of you, or at least 2 or 3 of you, have dealt with Lagrange polynomials before. I know it's been a while, but can anyone tell me what nice properties Lagrange polynomials have? Like, what makes a Lagrange polynomial a Lagrange polynomial? How do you how's it supposed to behave at these points? Well, I guess it was about a year ago when I mentioned this in 560, so I can't fault you if you don't remember. Like, what are the values? Okay, since there are Lagrange polynomials for these x values, what are Lagrange polynomials equal to at these points? The idea is to make the coefficients very easy to get. They're just function values. Because if I set x equal to xi, then I want this whole summation to turn out to be equal to ui. So basically picking out the function value that I want corresponding to the x that I put in here. So if I put an x1, I need to get u1. If I put an x2, I need to get u2.
I remember.
Uh-huh.
So we start with x1, for which it was just x. And then it had a constant that followed for x equals 2 and x equals 3.
Okay.
But that was in 685.
Oh.
And I was doing the vector discretization.
Okay. I can't be sure if you're not referring to something else. But since you use function values by coefficients, I want to make sure that if I plug in a certain x value, I get the corresponding u value. What does it say about what the Lagrange polynomials are supposed to be equal to at these points to make that happen?
Constant.
Oh, but what constant? That's the thing. Like, because the u's, they could be anything. It's supposed to work for whatever function I choose. So if I want to make sure that if I plug in x1, I'm going to get u1 and no other u's, then what does that say about what the Lagrange polynomial should be equal to? Like even in this specific case, Pn of x1 so I'm plugging in x1 into all of Lagrange polynomials, and the result is supposed to equal u1 corresponding to x1. So the only way that I can guarantee that this will happen, regardless of what the u values might be. Okay, so yeah, one of these should be equal to 1. What about the other ones?
Okay, at that point they will be 0.
Yes. Okay, so what we need is Lj of xi equal to 1 for delta. Yes. Equal to 1 if I is equal to j and 0 otherwise. Okay. Well, okay. I hope you do too. Right. Now, so there is a formula that makes that happen. So it's equal to a product so top of these linear factors x minus xi and xj minus xi for I not equal to j. So the idea is if I plug in x equal xj, I'll have xj minus xi over xj minus xi, and I get 1. I'll multiply together. If I plug in any other x value for my grid, like so xk, where k is not equal to j, one of these linear factors up top is going to be 0, causes the whole thing to be 0. So Lj has as its roots all the x values except for xj. The question about how this formula came about. So I want to use this approximation to get an approximate derivative of u of x. So now u prime of x is approximated by Pn prime of x okay. Try this, right? Okay. I'm going to plug in a specific x, Pn prime of x prime. So that's going to be sum over j. So same coefficients, uj, but then I have a derivative of Lj at xi, which I'm going to call dij. Because these are just numbers now. So another way of putting it is u prime evaluated the entire vector of x values is equal to some matrix capital D with entries dij times my vector of all my u values, because what I've written here is a matrix vector product, the matrix D times the vector u. So now what we have is a kind of like a finite difference, or just not, well, actually, not, it wasn't finite, well, either finite difference or a spectral periodic. But in most cases, we could describe numerical differentiation as a matrix vector multiplication. You have your vector of function values, you multiply it by your differentiation matrix, you get your approximate derivative values. Same thing here, where these are the entries of your matrix. So, for clarity, U is the vector consisting of the U values, U of x naught, U of x1, U of xn. Okay. In 460, we actually solved this before. I showed you two ways of deriving finite difference formulas for derivatives. So one way was to use Taylor series. And the other way is if you're trying to use function values and selected x values to approximate a derivative, you would construct the Lagrange polynomials for those x values, take their derivatives, and plug in the point where you want the derivative. And that gives you your coefficients. So these finite difference methods that you're used to, forward difference, backward difference, center difference, etc. Now, I derived them before using, well, actually, you know what? I actually did use the interpolation approach in this class. In 465-60, I show both approaches, deriving them using a Taylor series or using polynomial interpolation. In this class, when I did that, I did not use Lagrange. But you can find that in the 465-60 material. This is 9.1. My book. That discusses both approaches. So if you're trying to express like a derivative or an integral of a function in terms of the values of that function at select points, and trying to take a linear combination of them, the way you figure out the linear combination you need is to solve whatever problem it is. Integral over AB or derivative at a certain point. You solve that problem for the Lagrange polynomials, and that gets you your linear combination. Okay. Now, what I haven't shown you is anything along the lines of what does this turn out to be. There actually is a formula for it. Dij equal to, well, first I need to define this symbol. Aj is a product for all I not equal j of xj, oh, wait, k not equal to xj minus xk. All right. So once I have that, then I get ai over ha xi minus xj. These are the off-diagonal entries, so I not equal j. And then for I equal j, I have a sum j minus xk. Okay. I should mention that these formulas here for a differentiation matrix is valid for any choice of interpolation points. As long as they're distinct. Because that's, it had to be distinct for Lagrange interpolation anyway. So actually, everything that I've written on this board, okay, is actually not specific to Chebyshev. But if you're trying to approximate a derivative using polynomial interpolation for any choice of x values, this applies to all of that. So there's nothing I've written here that's Chebyshev specific, but I will get to that in a moment. By the way, a source that I've used for this is a book called Spectral Methods in MATLAB by Nick Trefethen. Trefethen is one of the most famous people in numerical analysis community, professor at Oxford, England, not Ole Miss. And he's actually my academic brother. We had the same advisor at Stanford, but many years apart. And he's written a lot of books, and this one's been pretty helpful. One thing that's unfortunate, though, so this formula can be found there, but there wasn't any substantive guidance on how to prove that this formula is correct, how to derive this formula from this definition right here. I once made an attempt at it, and honestly, I couldn't figure it out, so that was unfortunate. Still a little embarrassed by that, but there's a lot of things that have gone back and worked out, but not that one. Okay. Maybe someday when I have time. But don't have any students. Now, so like I said, this is for general interpolation points. When the points in question are the Chebyshev points, then it's possible to come up with somewhat simpler formulas. Because this one, unfortunately, involves a sum. So this right here is like not in closed form. That's actually in each of these products is expensive to compute. Because here in this case you have n+1 of these products to compute. Each one of these involves n factors to multiply. So it would take order n squared work to compute all of these, and then go ahead and fill in the matrix. All right. So now I'll show you, and this is something that you'll actually use in one of the homework problems. This will be problem 4. What this matrix D becomes in the Chebyshev case. Any questions about this board before I erase it? Okay. All right. But if you put your x values happen to be the Chebyshev points, then the matrix D has these entries. All right, what I'm going to show is there's certain formulas that apply to the first row, and last row, and first column, last column, and then in the interior. So for instance, for 1 entry, the upper left corner, for the square plus 1 over 6. And then the negative of that at the opposite corner. This corner we have 1/2 minus 1 to the n, and minus that at the opposite corner. So both entries worked out pretty nicely. Along the remainder of the first column, we have minus 1/2 minus 1 to the I over 1 minus xi. And then similar on the other end, somewhat. So plus 1/2 minus 1 to the n plus I over 1 plus xi. Okay, the rest of the first row, we have 2 minus 1 to the j. So as usual, I is a row index, j is a column index. J, and then down here, the sign changes from what's up above. Okay. So that's what we have along the fringes. In the interior, on just the main diagonal, this is a source of confusion last year for some students in the homework. You have so if on the j diagonal entry, so the jj entry, you have minus xj over 2, 1 minus xj squared. And then everywhere else in this middle portion of the matrix, with its off diagonal entry, you have minus 1 to the I plus j over xi minus xj. And then the same formula applies down here with the appropriate I and j. All right. And this is true for I and j going from 0 up to n. So this is an n plus 1 by n plus 1 matrix. So be careful about when you work with this in MATLAB. Of course, MATLAB uses 1-based indexing. So you need to translate these index values from 0 to n, how it's written here, to 1 to n plus 1 in your code. Like that would apply to your vector x of the x values. Now, but you also have to keep in mind here, I and j are used as indices, but here we're used as exponents. So, for example, in this expression, xi minus xj, let's suppose we're working with the second and third x values. So that'd be x1 minus x2, the way it's written here, because the indexing starts at 0. But that would be x parentheses 2 minus x parentheses 3 for second and third x values in your code. But in this part, the I and j should still be 1 and 2. So you have to distinguish, is I or j being used as an index, or is it being used as an exponent. But because for indices, everything shifts. For exponents, they don't. So, so be careful about how you code up these formulas to account for MATLAB's one-based indexing. For higher order derivatives, so for example, second derivative, you can use this matrix squared. And similar for higher order derivatives. So this matrix performs a single differentiation. Any power of it will give you the approximation of the appropriate higher order derivative. Dang it. Any questions about this monstrosity that you'll have to code later someday? Now, unfortunately, this can be pretty expensive. Because like, if you construct this matrix and then you use it to approximate a derivative, that's a matrix vector multiplication, that's over n squared operations. And these entries will generally be non-zero. Now, by contrast, if you make a matrix that carries out differentiation, like finite difference, like standard difference formula, for instance, that's order n operations because the matrix is so sparse. Here it's not sparse. But this is not the only way to carry out differentiation using Chebyshev points. So an alternative is actually using a tool from a periodic case, using the fast Fourier transform. And the reason for that is if I let x be equal to cosine theta, so x is the interval in the interval -1 to 1, theta is in the interval 0 to pi. Okay. Then, if u of x is a linear combination of Chebyshev polynomials, well, Tj of x is defined to be cosine of j inverse cosine of x. So this is a definition of a jth degree Chebyshev polynomial. Then I can replace x with cosine theta and now I have, instead of Tj of x, I have cosine of j times theta. So now I have a Fourier cosine series. I could use a Fourier, a discrete cosine transform. And so now I can compute a derivative of this using a fast Fourier transform like I discussed last time, to at least take a derivative with respect to theta and use a chain rule. So du dx is equal to u composed with cosine d theta d theta dx. Well, theta is inverse cosine of x, so I'd actually be multiplying by the derivative of arc cosine or inverse cosine. So that would actually be more efficient because I could use the fast Fourier transform that takes order n log n operations. Taking a derivative of this with respect to theta would be therefore be very quick. And then this post-processing multiplication would also be very quick. I have more detail about this in the notes. I'm not showing you all the details because I got the formulas from the source I mentioned earlier, the spectral methods from MATLAB by Trefethen. I'm not entirely convinced that all the formulas are correct. Like for example, I used the formulas there to try computing a derivative in an example, and in the interior of the interval it looked quite good, but at the boundary something went wrong. Oops. Fortunately, this approach is not something you'll be using in the homework anyway. But I wanted you to be aware of it, that even in the case of non-periodic boundary conditions, fast Fourier transform can be very helpful in computing accurate derivatives. So periodic or non-periodic, so D gives spectral accuracy. The word order 8 to the n accuracy, but as mentioned, n is proportional to 1 over h. So in other words, converging to 0 faster than any power of h if a function involved, the true function is smooth. So that's why we go to all this trouble, because we get so much more accuracy than using conventional finite difference methods. Okay. Some questions about what we have here? Okay. All right, so now what I have are some examples that show, like, once you make the matrix Dn, the matrix Dn. In the notes, I call it Dn, subscript for the however many grid points you have. Okay. All right. So I'll show you some examples in terms of how you can use this matrix to solve certain PDEs. Because for numerics, generally what we're doing is for time-independent problems and boundary value problems. You want to express, you discretize the PDE and obtain a system of linear equations. So basically, AX equals B problem. So it all goes down to what is the matrix? What is the right-hand side vector? Because once you have those things in MATLAB, you just use backslash and you solve your problem. So it's all about the setup. Okay, so first example, we'll have response equation. So in this case, we have uxx is e to the 4x on the interval -1 to 1. And then we'll have homogeneous Dirichlet boundary conditions. So u is equal to 0 on the boundaries. Okay. So then all you have to do, solve it numerically, and solve this system of equations where D n tilde squared is equal to, you take your matrix Dn, you go ahead and square it. And you delete the first and last rows and columns. And the reason for that is we're only solving for u in the interior because we know what u is on the boundary, it's 0. So the first and last columns correspond to the unknowns that are at the boundary points, but they're not unknowns in this case, they're known. The first and last rows correspond to equations where the PDE is enforced on the boundary. We don't need that either. So, but very important is square a matrix first, then delete first, last rows and columns. If you go the other way around, and this notation kind of suggests that you'll get the wrong result. All right, so square, then delete. Okay, the right-hand side vector f is e to the 4xj. So this is your right-hand side function evaluated at only the interior grid points. So the system you're solving is going to be n minus 1 by n minus 1 because the matrix Dn is n plus 1 by n plus 1, but you're tossing out 2 rows and 2 columns. So that's it. You solve a system, and then you have your solution at the interior grid points. Yeah, homework problem 4, you'll have a PD kind of like this, where you have a second derivative and a first derivative term. So you'd be using this matrix for second derivative term, and then just dn with the first and last rows and columns tossed for a first derivative term. And then I think your right-hand side for that problem is just equal to 1, by a vector of 1s, and then you just solve that. For second example, slight variation. Well, it's not an equation, but it's a nonlinear equation. U(x) equals e to the u. So the e to the u, where u is a solution, makes it nonlinear. And we'll still have u equals 0 on the boundary. Okay. So because the PDE is nonlinear, we're going to have a nonlinear system of equations to solve to get the solution. Okay, so we use what is called a fixed point iteration. So in the same matrix as before, dn tilde squared, u iterate k plus 1 is equal to a right-hand side vector where you take your previous iterate uk and evaluate it, plug it into the exponential to get to right-hand side. And you need an initial guess, u0. We'll just make that 0 because at least it satisfies the boundary conditions. So make an initial guess, plug it into here, solve this system, and then you get u1, you plug u1 in here, solve to get u2, and you just keep going. So this applies for k equals 0, 1, 2, until convergence, assuming it does converge. So when you have a nonlinear PDE, And chances are you need to use some sort of iteration like this to solve it. This is just one iteration you could use. You could also try something along the lines of like a Newton's method for a system, which might converge more rapidly. But at least here, this one is a lot simpler to set up. Question on this one, or either of these two? A few more. All 5, 6 materials going back to Hong Kong. All right. Next one is an eigenvalue problem. All right. So uxx is equal to lambda u, same spatial domain, same boundary conditions, homogeneous Dirichlet conditions. Okay. All right. So what you can do is you have like MATLAB compute the eigenvalues and the eigenvectors of the matrix from the last previous examples to get until the square. All right, so the command in MATLAB I do something as VL is equal to I of let's call this matrix variable named D2. So what happens here is each column is a solution of this PDE. And this matrix L, this is a diagonal matrix. The diagonal entries are your values of lambda. Okay. So for example, if you look at the 1, 1 entry of this matrix L and the first column of V, so the first column of V is your solution U of a PDE with lambda equal to the 1, 1 entry of L. Now, all of these examples I've shown you are one-dimensional. Here's a 2D problem. So still Poissons, uxx plus uyy, so Laplacian is equal to some given function f of xy. And so your domain omega is the square x and y between -1 and 1. And then same boundary conditions. U equals 0 on the boundary. So then the system of equations that you solve is ln u is equal to f, where the matrix ln in this case is you're going to take Kronecker products of identity with the matrix from the preceding examples, the dn tilde squared. So the second order matrix without the boundary rows and columns, plus the same Kronecker product in reverse order. So the idea is that depending on how you order the grid points, so one of these is a matrix for second partial derivative with respect to x, and then the other will be second partial derivative with respect to y. And then if you evaluate your function f on your grid points and then reshape it into a vector, that would be your right-hand side. And then when you solve this, you'll get a vector u that consists of the values of your solution on this your grid of Chebyshev points. Then you would reshape that vector into a matrix if you want to, for instance, visualize your solution on a Chebyshev grid. So, so you're computing a solution on a non-equally spaced grid because the Chebyshev points are not equally spaced. Okay, now, as for how this would go in MATLAB, when you get to homework problem number 7, that one is a two-dimensional problem. What you can do is all right, so you can let x be a vector of your Chebyshev points. And then use MATLAB's function mesh grid. And what you do is you pass the vector of x values and a vector of y values. In this case, it would be the same vector, x. And this will return matrices, a matrix of x values and a matrix of y values that are all of your grid points in this two-dimensional grid. So it's like taking a Cartesian product, basically, to get x and y values. And then, then what you can do is reshape into a column vector. This syntax, where you take the matrix you want to reshape and an empty set of square brackets and then a 1, we'll reshape it into a column vector, or you could do this, x2 parentheses colon, that will do it too. It gives you a column vector. And then y2, same thing, get it as a column vector. And then you can, if you have your MATLAB, like a MATLAB function handle for f, you can evaluate it at x2 and y2 to get your right-hand side vector. And then what you can do is you can form this matrix, and then for the product you can use the MATLAB function cron. So cron of identity and this matrix, like I called it D2 earlier, and then cron of D2 and identity to form your matrix, and then just use backslash and there's your solution. The solution will be a vector, but you can reshape it into like an n-1 by n-1 matrix to display it. Okay, questions about this one? So now the $64,000 question is, when are y'all going to do some homework? I mean, I know I'm loose about deadlines, so I invite this. And which of course that means that other classes get bumped up. Of course, you can do this in 2 classes though. I don't recall if you are or not, but yeah. I thought of a situation where I'm asking this about the same thing in November. So yeah, because some of these problems, the MATLAB coding part, can be a real pain. Although once you get through, like, so you know, problem 2, the first MATLAB problem, So that's where you first start working with these things, and that can be a bit of a pain, but then you end up performing similar tasks in later problems, and it's not as bad. But sometimes there are tedious things to work out. For example, in some problems, you need to work out, like on paper, what is the exact solution of a PDE, so that you can compare your numerical solution for it to it and examine the error. Like if you have a method that's second order accurate, one of the tasks is to confirm that your solution method really is second order accurate. So you want to have an exact solution for that. So uh, I mean, 'cause I also know, like, you're all GTAs too, and teaching and or tutoring. So I know it's taking up time soon, but let's not let it sit too long. So I'll just keep nagging you about this now and then, and annoying you into doing it. So yeah, whatever works, right? So, okay. Um, but in the meantime, I guess that's it. So that's the end for spectral methods. I'm gonna do like numerical linear algebra aspects of this uh, next week, unless y'all get some homework questions.